Morning. I am Krishna Kumar from Krishna's classroom. We continue with our lectures on Riemann Stieltjes integral. In fact, the third part of it. Now we have just recalled the basic assumptions. AB is a compact subinterval of the real line. F is a real valued function which is bounded on AB, and we have the lower bound given by small m and the upper bound given by capital M, and then alpha is a monotonically increasing function, that is alpha x less than or equal to alpha y whenever xy belongs to AB with x less than y. Now these are the basic assumptions, and this is where we start from. We have already seen that, we have explored this, defined what is meant by the Riemann integrability of f with respect to alpha. And this is what is called the Riemann Stieltjes integral. Now the basic condition for integrability in this case is, of course, we use this notation delta alpha I by as. Okay, so let me, for a partition P x naught B, we define delta alpha I alpha xi minus alpha minus 1 increasing, let me put here increasing. So you know that this is greater than or equal to 0, and we say that f belongs to R alpha or Riemann integrable alpha if the following is true. There exists a partition P of AB such that given epsilon, there exists a partition P of AB such that the upper sum where UPF and LPF we have defined earlier, and UPF and small mi delta where mi is supremum of f x belonging to xi minus 1 xi small mi equal to infimum of so this is a necessary and sufficient condition for f to be Riemann integrable with respect to alpha. Now we explore which functions are Riemann integrable. In fact, we found a very rich class of functions which are Riemann integrable. We found that all continuous functions on the interval AB are Riemann integrable with respect to alpha. We also proved that if f is monotonic with continuity assumed at all points of discontinuity of alpha, then it is Riemann integrable with respect to alpha. Now this class of functions, now this theorem suggests that there is a very large class of functions which satisfy these conditions. So what we now explore is the same problem in a different direction. And what we look at is the following. See, we have the interval AB, and suppose phi is a function defined from AB to R. So phi is a function, is a continuous function. F is as defined above. Range of f is contained in by the assumption that f is bounded. And now let phi be a function defined from the interval m, capital M to R. We assume phi is continuous. Then observe that a function h from AB to R is defined by that is hx equal to phi of f of x. Now h is defined from AB to phi. So the composition of phi and f. Now what we ask is the following. Suppose f is R alpha and phi is continuous on the interval m to n. Then is the composition of these two functions, namely h, R alpha. So we will ask this question, and the answer to the question is given in the following theorem. Then h so h is now defined from AB to R, and what we prove is that h is a Riemann integrable function with respect to time. Okay, let us explore this. Proof of this. So when you work out the proof of this theorem, first of all, be clear about what is given. What is given? F belongs to R alpha, that is given, and the continuity of phi. These are the two things that are given. Okay, so let us translate this. F is continuous. Okay, so we start with phi. Phi is continuous on M, implies given epsilon positives, there exists a delta 1 positive such that mod phi t minus less than epsilon whenever E comma S belongs to Mn and mod P minus S is less than F. So this follows from the continuity. So this is given. This is one of the given things that we use. Now we define delta as follows. Delta is less than or equal to less than minimum of delta 1 and so we already have epsilon is the given arbitrary number. There is a corresponding delta 1. choose delta as this. Therefore, you are assured that delta is less than epsilon. So, the implication is that delta is less than epsilon. Now we use the next assumption. What is the next assumption? F belongs to R alpha implies given epsilon, okay, there exists a partition P B of AB such that the difference between the upper sum and the lower sum, that is U E F alpha minus L alpha less than delta square. So we have from here epsilon corresponding delta 1 and delta we have chosen, and for that delta square there is a corresponding partition which satisfies this condition. Since for any arbitrary epsilon there is such a partition, so this is true. So we choose the partition corresponding to delta square. So we shall use this later. Okay. Now what do we want to prove? So these are the basic assumptions translated into workable form. Now what we want to prove is to prove that H, which is equal to phi composition F, belongs to, so this is what you want to. Okay, so let us bring in some notations which we want to work on this. Okay, so I'll just take this out, and then we have so let that is associated with F. Now we define, let Mi star defined as supremum of H for X belonging to psi both the supremum and the infimum exist. There is no problem. Okay. Now let us see what exactly you have done. See, to begin with, you have an interval. Now we have a partition x0, x1, xi minus 1 to xi, xn minus 1, X. That's a partition available on the interval A. F is defined on this. F is defined on this. H is also defined on this, but H gets defined through a map. What is a map? See, you have a map. See, there is a map from here to. Okay, there is a map from the interval M to capital M, and you have got this is the phi map. So F is a map from here to R. Okay, so you have the composition F composition. Sorry, phi composition F. This is given by H. This is. What more you have? Once you have a partition here, now you have a map alpha from here. Alpha is a monotonic function. So that means you have got alpha x naught, alpha xn, and this is alpha xi. Now alpha xi to, see, this distance is denoted by alpha. This distance is what you call delta alpha. So you define a new distance notion between xi minus 1 and xi given by delta alpha. So these maps, and now this is what you, this is the situation that you have. This is alpha x1, this is what you have. So this is interval M2. Okay. Now what we are asserting is that the function, mark this wrong, sorry. Yeah, it's right. Okay, phi, the composition of phi with F is what you call H. So it's a map from the interval AB to R. H is also a map given from here to here. Phi is from here. So phi is a map from here. Just mistake. Yes, that's right. Sorry, I think I made a mistake. Yes. So this is a diagram. F is a map from AB to M, and phi is a map from MM to R. We are assuming phi is continuous, and F is R alpha. The question is the composition map F of F and phi and F is this R alpha. Okay, fine. So that's right. Now, what you have is that there is a partition on the interval AB that induces a partition on the interval M to M through alpha. And you are working on the distance between two adjacent points of this, and it is denoted by delta alpha I. And what one has is that, see, Mi, so the upper and lower bounds of F are given by this, and upper and lower bounds of H are given by Mi star. This is the situation. So that describes it. Now, what is that you want to prove? You are expecting H to be R alpha. So H, let us write down what it is. H belongs to R alpha if and only if given epsilon positive, there exists a partition P1 of such that U P1 F alpha minus L P1 is less than. This is what we want to prove. So we have to assert or show the existence of a partition of the interval AB in this form. Now let us start working on this. Now we are going to prove that in fact P1 can be chosen as P1. The same P works for, there is a P that we already have. What is that P? That P is associated with F delta square and the Riemann integrability of F with respect to alpha. So this is what defines P. Okay. So let P1 we take P1 as P. Now for P that appears in the Riemann integrability of Riemann integrability of f alpha serves the purpose to h belongs to. Okay. Now we have to essentially deal with this inequality. Now let us take xi. So we take or we split the indices 1 to n into two classes. Say, so we write 1, 2, where A is defined as a set of all I, for which and B as the collection of I for which so that covers all the integers from 1 to n. Now you see that A intersection B is empty, right? Therefore, now let us look at this sum. That is UPH alpha minus NPH alpha for, see, let us write this. What is this? This is equal to, we'll split into two parts. One, I belonging to A of mi star minus mi star into delta alpha I plus that alpha as we have defined here. It is alpha xi minus alpha xi. So this is the sum value. Now we estimate each one of them separately so that we can get an estimate of this. So first consider we already know that. What can you say about mi star minus small mi star? Because we know that, see, see, the condition that you have is mi minus mi is less than delta. So what does it mean? If mi minus mi is less than delta, see, for Ts belonging to xi, I belonging to. This is the condition that you have. Therefore, phi of this is what? So H you get mi star minus mi star. This will be mi star will be some at least it's equal to some phi of some fs, and this is phi of some small mi star is going to be some st, and we have phi continuous. Therefore, if this is less than delta, then you have the following, that this is less than. So using continuity of therefore, what do you have? So we have this is less than epsilon, implies sigma is less than or equal to summation over I belonging to A. This is less than epsilon, which is less than or equal to epsilon times sigma delta alpha I. Now I running from 1 to n, which is equal to epsilon into alpha b minus alpha. So this is given by. Okay. So that's about the sum for I belonging to A. Now we do the same thing for I belonging to B. For I belonging to B, let us work this out. So we are assuming that mi minus mi greater than or equal to that. That's our assumption. Okay. So we will make some computations. The computations are the following. Okay. So we want to estimate alpha. Okay. So let us do that. Now delta times sigma delta alpha I b. This is of course less than or equal to I belong to this. Why? Because mi minus mi is greater than or equal to delta. Therefore, delta is a lower bound for mi minus mi. So this is since That's it. Okay. Now what about this? Now this is less than or equal to summation over I 1 to n what about this? This is essentially, because we have just added a few terms, additional terms which are positive or not negative. Therefore, the inequality does not change. This you know is here we are using the Riemann integrability of f. So what you get? So here you get this is less than or equal to, or this is the sum. This is equal to u p f alpha minus alpha, which you know by choice the partition has been so chosen such that this is delta square, less than delta square. Therefore, implies is less than, since delta is not equal to 0, cancel. Okay, so delta cancels out. So okay, that's an estimate for that. Now we can use this to estimate the following. So we have two informations readily available now. So let us write down this. So therefore now we write UPF alpha minus U I belonging to A of Mi star minus Mi star delta alpha I plus sigma I belonging to B and each of which we can estimate now. So the first term that appears there is less than or equal to, see, Mi star minus Mi star is 2k, so this is less than or equal to see sigma delta alpha I. So I can write this the first term. Okay, so we get this. We estimated this first term. This one is estimated to be Mi star minus Mi star is less than epsilon. Therefore, you get this this epsilon times alpha b minus alpha a. That estimate we already have. Then the second term, we get the estimate of this is, you see, Mi star. So let us take Hx. So Hx be less than or equal to k for x belonging to U. This is bounded. Okay, therefore let k be the bound of that. Therefore this is less than or equal to 2k times sigma phi. And therefore this is less than or equal to and this part we have already estimated. Summation over I delta alpha I is less than delta, and this is delta which is less than or equal to, because we have chosen delta in such a way that delta is less than epsilon. Therefore this is epsilon therefore this is equal to which is a constant. So this is something like that is which is equal to some m tilde times where m tilde equal to alpha b, which is a constant, and therefore you see that we get UPH alpha minus LPH alpha is less than or equal to m tilde epsilon. So, arbitrary choice of epsilon. Which implies H belongs to that's a proof. So let us just have a understanding of this. What does this say? See, you have the interval, see, x naught, xn, xi minus 1, xi. Now, if this interval belongs to, okay, if I belongs to A, then we have an estimate for that. Okay, what is that? You have mi star minus mi star, small mi star delta alpha I is bounded by epsilon times alpha b minus alpha I. Now that is what we have. Suppose I belongs to B. Look at all those I for which this belongs to B, and for that you look at this one. The whole thing is less than delta. That's what you have. Okay? The length of the whole thing is less than delta. Right? And that is of course less than yes. So what happens is the intervals on which you have the condition that f differs by mi minus mi. So we are assuming if mi differs by mi minus mi and mi minus mi is greater than or equal to delta, is the total length of that interval is less than delta, which is less than epsilon. So that is the one that we are using. Okay? Because see, you go from AB to capital M, xi, then alpha is the map. So you have alpha xi minus 1 and alpha xi and the length of this interval. So we are talking about for I belonging to B, length of such intervals together are less than epsilon. Okay, so we work with that, and on that, on such intervals anyway, the function h is bounded by 2k, right? Sorry, yeah. What you have is h, mi star minus small mi star is bounded by 2k. So you get this second estimate, and that completes the proof. So, having proved this theorem, now you can ask the general question: which functions are Riemann integrable with respect to alpha? This is a question that is a generalized question that you have, more general question that you ask. See, there earlier when we were discussing Riemann integration, we didn't have this alpha coming there. There alpha x was taken as x, a nice linear function which is continuous on the interval AB and so on. But there was no problem working with that. And there we have even characterized the functions which are Riemann integrable. There we said that it is the set of if the set of discontinuities of the function form a null set, then you have Riemann integrable. You have a similar sort of situation that would emerge, but we will have to wait until we go to measure theory and so on. So here we have actually rigged the distance between xi and xi minus 1 and xi. We have now redefined it as alpha xi minus alpha xi minus 1 for a monotonic function alpha. Therefore, a lot of things can happen. See, look at this map. Suppose alpha is constant. Then what happens? The whole AB, or you take any xi minus 1, xi, then what you have? You see that it goes to the both these points xi minus 1 and xi map to the same point, and therefore delta alpha I is equal to 0. Okay. In other words, now we are attributing a new concept of length on the interval AB. That is, for intervals here, you have a new concept of length that is it may be 0 even when the interval is not reducing to just a point. Okay. So some versatility has been brought into the scenario. The other scenario that comes is alpha is discontinuity. Let's say x naught, say xi. Then what happens? You take AB and take the point xi. Now you see that xi minus 1 minus 0 is a point here, but alpha xi will be a different point. Okay. So there is some measure coming out here. Okay. So associated with this point xi, now you are going to have a new concept of length, or some weight is attached to that point. Now this is something that you have. So you have sort of new length for length of zero. These two may differ because that's why you have a discontinuity. So there is some positive length attached to points here. Wherever there is a discontinuity, there is a corresponding definition of the length of those singleton points attached to it, as we shall see soon how this manifests and how this is useful in our analysis. So we'll see that. Okay. Now we just recall some of the results that we had in the Riemann integration case, which are the properties of the integral. I am not going to prove any one of them because they are similar to what we did earlier, except that we use a particular alpha into the picture. So properties of the integral. The first part of this is that f1 belongs to R alpha, f2 belongs to R alpha, implies f1 plus f2 belongs to R. So also, if f belongs to R alpha, then Cf belongs to R alpha, for C a constant. That's quite easy to prove because you will be working almost routine work with the upper sum and the lower sum. Now, the only thing that you have to bring in is alpha should be brought into the picture. Okay. The second property is that if x on AB Ft belongs to then integral f d alpha less than or equal to integral that's what it is. See, the first property tells you that it's a real vector space. R alpha is a real vector space. the addition and scalar multiplication will define them. The third property is that f belongs to R alpha on AB and A less than C. That is, C is a point that lies between A and B. Then you can actually split the integral. The splitting is okay. Then f belongs to R alpha on AC. F belongs to R alpha on CB. And f belongs to and integral of a to b f d alpha equal to integral a to c f d alpha plus integral c to d f d. This is again easy to prove. You can prove that for any c on the interval or any subinterval of ab, then this function is Riemann, and then you can also see that the two integrals add up. All these you can take as exercise. That's an upper bound for this integral. 5 then first statement is that f belongs to positive constant then integral a to b f c alpha equal to then we assert that f belongs to C alpha and integral a to b f b c alpha equal to c times integral a to b f b. So these are some of the properties that you can prove. I leave the exercise to prove each one of this to you, because some of them I have already proved in the special case where alpha is equal to alpha x is equal to x. So I just omit the proof of all this. Okay. Leave it as exercises. Now an interesting result that we can get immediately from the previous theorem that we proved is the following. I think I have mentioned this in the earlier case also. If f belongs to R alpha and G belongs to, then fg belongs to R alpha and mod f belongs to R alpha. Further, mod integral a to b f b alpha is less than or equal to integral a to b mod f. An important inequality that we normally have. Okay, just make some mention about this proof. Proof of this result. The first result that we do is the following. We first observe that f belongs to R alpha implies f square belongs to R. How do you prove that? So choose G, choose phi x equal to x square or phi p equal to p square. Now you take phi composition f, which in turn is f square, and apply this. The second part is coming to, we use the inequality and use the identity. For fg is equal to f plus g whole square minus f minus t whole square. Now you can, if f is R alpha, g is R alpha, f plus g is R alpha, therefore f plus g whole square is R alpha. So also f is R alpha, g is R alpha means minus g is also R alpha. Therefore f minus g is R alpha. Therefore f minus g whole square is R alpha. And this is actually and that implies f minus g whole square is R alpha, means minus of f minus g whole square is R alpha. So now add the two, you get 4fg is R alpha, which in turn implies fg is R alpha. So that's very simple to prove. Okay, right. The next thing, that is the choose Then using this, you get what you get, phi h equal to, yeah, phi of now use the theorem that we have proved earlier. F is R alpha, phi is continuous, therefore this is R. Okay, and what you get is that now we choose C, which is equal to plus or minus 1. So that C times is greater than 1. So you may have to choose plus 1 or minus 1 depending on which is to make this greater than or equal to 0. Then mod integral, this is a technically improved actually, d alpha is equal to C times integral f d alpha. Now this is equal to integral Cf d alpha. This is less than or equal to integral mod f. So that proves. Since Cf is less than or equal to, that completes the proof. Okay. So I think I'll stop today and then start taking up what are called discontinuous jump functions, okay, or what you call functions which have a discontinuity at a point, otherwise constant. Okay. So we will explore that in the next lecture. So thank you very much.